Okay, so the first problem is we have these two masses, both of mass m, connected by a spring with spring constant k. And so we want, if they're stretched and then released, then we want to find the frequency of the oscillation of this system. So for this problem, I'm actually going to do, if there are two not necessarily equal masses, m1 and m2, because it's more insightful. And then you can just plug in m1 equals m2 at the end. So anyway, if we look at the center of mass, which is say somewhere here, and then the distances to each separate mass are x1 and x2, then we want to find, first we want to find this d squared x1 plus x2 over dt squared. Basically, this gives us the acceleration. And if we can write this as k over m times x, then the frequency is omega equals square root k over m. And so this first part, the k over m times x is the acceleration, and you can see for yourself how omega equals square root k over m comes from that. Okay, so now if we look at these two masses, we see that there is the same force, let's call it F, acting on both of them. The force acting on both of these masses has to be also F m1 times d squared x1 over dt squared, which is the acceleration. And this has to be equal to m2 times d squared x2 over dt squared. So then we could get that F over m1 is equal to d squared x1 over dt squared. Similarly, F over m2 is equal to d squared x2 over dt squared. Okay, so now we can just add these two equations together, which gives us F times 1 over m1 plus 1 over m2 is equal to d squared x1 plus x2 over dt squared. So now we know that this F is for the entire system, and for a spring, the force is F is just equal to kx. In this case, it would just be the length of the entire spring, x1 plus x2. So then we have this thing. We have kx1 plus x2 times m1 plus m2 over m1 m2 is equal to this d squared x1 plus x2 over dt squared as before. So now we can change this. So now we can look at this expression in the form of k over m times x. In this case, x would of course be x1 plus x2. It would be x1 plus x2 because that's the same expression that appears in the d squared x1 plus x2 over dt squared part. So then this means that omega would be equal to square root k over this m equivalent mass, which is of course m1 plus, which is of course m1 m2 over m1 plus m2. So this would just be equal to k times m1 plus m2 over m1 m2, and we have to take the square root of that. And if we look at the original problem, which has m1 equals m2, this would just be equal to square root of 2k over m. So yeah, that's the answer to the first problem. One whistle has a pitch exactly one octave above the other, which basically means it has twice the frequency, and we want to find the temperature of the air in whistle B. Okay, so basically in wave theory, we just have this equation, which is that v is equal to f times lambda, which is the wavelength, v is the velocity, of course, and f is the frequency. So this means that f is equal to v over lambda. So now this lambda has the form of 2L over n. And L is the length of the width. So, and in this problem, the two lengths are the same, so we don't need to consider that. And n is just some number. It's like some integer. It can be a lot of different integers. So then we know now that f only depends on v. And so v is basically this p over rho, where p is the pressure and rho is the density. And you can verify for yourself using dimensional analysis that this is indeed equal to the velocity. So then we want to find this v's relationship with the temperature. And so to find this, we apply the ideal gas law. PV is equal to nRT. So if we do this, then rho is equal to, let's say, n times m over v, where m is the mass of the is the mass of the mole of the this gas, because n is the amount of gas in moles. So then this is because v is the volume, and so n times m would just be the mass. So this would be the density. And so then this is equal to, if we look at n over v, we can see is equal to p over RT. So then this times m, so this times n is m would be equal to the density. And so then, of course, you can also see that P is equal to nRT over V. So then P over rho would be nRT over V times P over RT times M. And this is equal to N times R squared T squared over PVM. But we can also, if you look back at the equation, at the ideal gas law, you see that nRT over PV is equal to 1. So then part of this can be canceled out. We get that this is just equal to RT over M, I believe. Yeah. So then, of course, the V is equal to the square root of this. So then V is proportional to square root T. And that means that F is also proportional to square root T. So now we have the relationship between the frequency and the temperature, so it becomes pretty easy to solve. Whistle A's air temperature, TA, is just equal to 273 minus 180, because we have to convert it into Kelvin. And this is equal to 93 degrees. And okay, and then so we know that the temperature of whistle B has to be 4 times higher than the temperature of whistle A, because we have to take the square root of that to get a frequency that is twice as high. So this would be 93 times 4, which is equal to 372 degrees Kelvin. So then to convert this back into Celsius, we just subtract 273. So this is equal to 99 degrees Celsius. So that's the answer for the second problem. Does anyone have any questions? Okay then, since it appears that no one has any questions, that's it for me then.